Hello from the Johnson Space Center. I'm Ron Dipfler, and today my colleague Julia Badger and I will be demonstrating Robonaut 2 for you. This is Robonaut 2, or as we like to call it, R2. Robonaut 2 is the first human-like robot ever to go into space, and there is a version that looks just like this robot currently on the space station working with crew. Robonaut actually has been a program here at the Johnson Space Center since the late 1990s. This is actually the second generation, which is why we call it Robonaut 2. First one, Robonaut 1, was built up in the late 1990s, and we used it all the way through 2006, exploring different ways people can work directly with robots. The whole concept behind Robonaut is that it can work with the same tools and the same interfaces and work in the same areas that people can work with, so that it can work alongside with people, helping them perform their tasks. This is very important in space, where you don't have as many people available to help you, so having a human-like robot is a great benefit. During 2006, when we finished up our activities with Robonaut 1, the General Motors Corporation approached us, and they were also looking for a robotic system that can help with tasks that currently only humans can perform. In their case, they were interested in tasks that their factory workers currently perform that are tiring or are ergonomically, that is, difficult to perform with human hands and can be stressful over time. So the Johnson Space Center, the NASA Johnson Space Center, and General Motors decided that together we could build a better second-generation version of Robonaut by pooling our resources. Now we're going to start today by giving you an idea of how Robonaut 2 runs, its range of motion, the different joints it has, how fast it goes, and then I'm going to tell you a little bit more about how it's made and what parts it has on the inside. This copy of Robonaut will never go to space, but we think it wants to go, and you'll see so in a moment. Now, Robonaut is very different from the type of robot you'd find in a factory, an industrial robot. Unlike those robots, Robonaut 2 is very soft. It has to its arms, and it has a nice soft skin covering it. All this makes it comfortable to work around. As a matter of fact, because it has these springs built into the arm, we're able to figure out how much force is at each joint, and we can then control that force at the hand. And this is very important. It allows us to basically make the hand act like a spring. It can move back and forth, and then it will always want to come back to the same location. This is very valuable if you're replacing something on the space station or even on Earth. You want the robot to give, as you're inserting something, like this direction, it will give in the other direction, so it goes in nice and smoothly. Also, this robot arm has one more joint than it needs to hold something in space. This allows our elbow to move with our hand roughly staying in the same place. And it's nice and soft, so if the elbow comes in contact with something as you're performing a task, it will move out of the way. But just like a human, we could stiffen up the elbow and get leverage off of it if we need it for the task we're performing. So now it's considerably harder to move. That's an example of when we actually want to react off of our elbow. Because of the extra joint, we know about the obstacles in our environment. We can actually move the elbow and keep the hand in place as we're performing our task. Now, putting a robot on space station was a very big endeavor. One of the most important things about it was making sure that everything was safe. We have a very large robot with a very large wingspan, and the crew has to be comfortable working around that robot. So we designed the way in which it's controlled so that it is comfortable to work around. We only give it the capability to exert enough force to perform the task at hand. If it comes in contact with something, it will just stop because that's a force beyond what it needs to perform its task. Julia's going to run a demonstration now of the robot running through a motion where it's given just enough force to perform that motion. And then we're going to run it a second time, and I'm going to get in the way of the robot, and you'll see what happens when it comes in contact with me. So imagine me on station not paying attention to the robot, and it bumps into me. Oh, excuse me. Since it is a human-like robot, we have to say excuse me, of course. And it is very easy. With just one hand, or even a few fingers of my hand, I can restrain it. And it won't continue its task until this arm is able to catch up with the first arm. And as a matter of fact, we can stop it anywhere along its task, as you'll see here in a moment. Being able to stop at any point makes it a very comfortable robot to work around. The crew feels comfortable working next to it as they perform their tasks. One of the big changes we made going from Robonaut 1 to Robonaut 2 is that we modified the thumb to make it more human-like. On Robonaut 1, the thumb only had 3 joints. That gave us quite a good capability on Robonaut 1, but we wanted to do better with Robonaut 2. Now we have a 4th joint that we've added to the thumb. This allows the thumb to come in contact with the other fingers to a much greater extent. By doing that, we can form a wider range of grasps and work with more tools and more of the other types of devices that people work with. We'll show you that right now. You'll be able to see Robonaut come in contact with this ring and pinky finger in a way that Robonaut 1 never could. Now, a few moments ago, I showed you how we can set the stiffness of the hand, that we can move the arm around as we're performing a task, or as the robot comes in contact with the environment, the arm just naturally gives that's doing something. We can do a similar thing with the fingers. The fingers actually have tendons that run into the forearm of the robot, kind of like the same way we're built. By measuring the tendon tension, how much force is on those tendons, we can control that force, and by doing that, we can control the stiffness of the fingers. So, if we're performing a task where we have to have a nice, sturdy grasp on a tool, for example, we can make the fingers nice and stiff, allowing us to maintain that grasp. But if we're dealing with a delicate science sample, for example, we want it to be very delicate. We want small position errors to not generate much of a force so that whatever we're holding is protected. We're going to show you that right now, how we can press on the fingers and they give in a similar way that the hand did earlier. So I can press on the finger, and it gives. This is relatively a stiff grasp, relatively stiff grasp. We're going to adjust that now and make it a bit softer to simulate the case if we were holding something very delicate. So now I can move it, and it's almost like in what we call a zero-G mode. It'll float, and it takes very little force to move it around, while the middle finger is maintaining that nice stiff grasp. So this shows we can adjust the stiffness of our fingers depending on the task we're performing. Thanks, Julia. Now, also, we have built into the fingertips, and actually we can have them everywhere on the hand, very, very tiny sensors that measure the force of what the finger is touching. So if we want to touch something very lightly, we can confirm that as we're making contact. One way to show that is I have a nickel in my hand here. I'm going to place it on the finger, and Julia's going to describe what happens.
So when you place it on the finger, we actually see that there was a line here where it was, and then when you put it on the finger, the line went down, and the nickel only weighs 6 grams, so it's very interesting and cool that the sensor can pick that up. And actually, Ron, can you pick the nickel off of the finger in just 1 second so that they can get a good view of it? There you go, right there. And put it on one more time. You see the big jumps? That's what we're trying to show with the very sensitive sensors.
Now, one of the most important interests that both NASA and General Motors shared with the robot in our development of the robot is that it's one that's designed to do work, to work directly with people, work side by side with people, and to be able to do that, we have to have a significant payload, be able to generate a significant force. For the case of space station, you have to be able to exert as much as 20 pounds of force to remove and reinsert different items on the station. And we're going to work with a 20-pound weight now in what is probably one of the most difficult configurations for a person to work with that kind of weight, to show you how strong Robonaut is. Now, sometimes we have a human compete with the robot, and that's actually quite challenging. While the robot is designed not to have a very high peak strength, that is, a person could exert a very large weight for a very short period of time, we've designed the robot so it doesn't do that. Instead, we have it so that it can exert a significant weight, for example, 20 pounds, or a significant force, for a very long period of time. You'll see that here in this demonstration. Imagine trying to hold a 20-pound weight like that. It's not easy. But for Robonaut, it can hold that weight for a very long period of time. So that was really cool. So we've shown you how Robonaut moves through space, the different joints it has, roughly how quickly it can move, how we control forces both on the arm and in the hands, and also how strong it is. And all that's really interesting and really cool about the robot, but what can it do in terms of tasks? That's the really important thing. Here we have an example of material we use throughout the space station. It's called a space blanket material. Actually, it's very similar to what the astronauts have on their space suits. Using Robonaut's dexterity and ability to move its fingers and how we control force, we're going to remove this space blanket and obtain another flexible material that's underneath there, and then I'm going to interact with the robot using its vision. Now, watch as it moves this space blanket material out of the way. You'll note that it does it in a very human-like fashion. Just slips it right out of the way. Now, you'll note on one of Julia's monitors the robot's looking at the envelope. And the way we know it's looking at the envelope is that it's painted green for us in the screen. Now, one of the best things about Robonaut being a helper for people is that it will hold that envelope there for me all day long. Great helper. So when I'm ready, I will put my hand over the envelope so the robot will know visually that I want it, and then it will let go. And I can wait a while if I like to, but we'll move things along a little bit. Put my hand right there, just lets go, and we can see what's in the envelope. Here we have a picture of the crew, the Space Shuttle Discovery that brought the Robonaut that's currently on space station into orbit. We also have a picture that represents our theme, people and robots working together. Now you just saw one way that people and robots can work together without using verbal information. The robot could see that I wanted the envelope and then it let go. There are other ways in which the robot can interact with the person without verbal communication to know what the person wants to do. For example, here, the robot's going to put itself in what we call a handshake pose. And it will sit there and wait until I come over and I start pumping the arm, indicating I want to shake hands. When I do that, it will close the hand and start shaking hands with me, and also turn a little bit more towards the camera and have its picture taken. It always likes to have its picture taken. Now, before I showed you how we limit the forces on the robot so it's comfortable to work around, well, that's only one part of the safety system we have on the robot. We also have the ability to constantly monitor the force the robot feels and the change in force the robot feels. What this means is that if the robot ever comes in contact with something suddenly, it will immediately turn itself off. That's a very important safety feature. If you have an inadvertent contact, you want to be sure the robot puts itself in a safe state. As a matter of fact, we have built that in so well on the robot on space station, we actually don't have to have what's called an emergency stop. Julia's going to show you what an emergency stop looks like right there in the view. This is what we call the big red button. We actually don't have to have one on space station. We actually have a yellow button, which we call a motion stop. And the crew can use that at their convenience for stopping the robot whenever they feel like it. But they have another way to stop it. If they come over to the robot and they actually simulate the robot coming in contact with something suddenly, they can turn off the robot with just a sudden change in force, just like that. And the blue lights that were on a moment ago turn off, indicating that the motor power is now off on the robot, and you can work next to it without any concern. The robot on space station has gone through a series of tests so far. We've checked it out, we've confirmed that all the systems are working properly, and it's now started to interact with the crew. It's done a handshake with the space station commander, who as a matter of fact said that it had a nice firm handshake. It has also started working with its first tool. But because NASA has such an important educational component to its mission, we also had the robot use sign language to say hello to the entire world. And we're going to demonstrate that here. And you actually need pinkies to say hello world in this version of American Sign Language. So that concludes our basic demonstration of the robot. Now Julia and I will take questions from anyone in the audience who would like to learn more about the system.
Can Robonaut talk?
When we put it in a certain mode where we actually have somebody wearing teleoperation gear, they wear a helmet so they can see through Robonaut's eyes, and they wear gloves so that they can move Robonaut's hands, and Robonaut talks to that person, and that person can command Robonaut with their voice as well.
Hi, I'm Anna Lyles. Can a Robonaut understand what you say?
Yes, there's different ways that R2 can understand the intentions or the desires of the astronauts. The handshake was one of them. It can use its vision sometimes to be able to pick up on gestures and motions that the humans are doing. For example, we have one demonstration where a Robonaut can decide to either fist bump or handshake, depending on what the human does when it approaches him.
How is Robonaut made?
The robot you see behind me, we started building it in February of 2007. We had the first arm ready in December of 2007, and the full robot was functioning in April of 2008. So it took us a little over a year to build up a full robot. And it required a whole group of engineers and computer scientists working together. Some building mechanical parts, the bones of the robot, others working on the electronics so the robot could see and be able to measure sensor data and be able to work with that data, and then software engineers to help program the robot so it knew how to respond properly when we gave it commands. There's a lot involved in putting together a robot like this.
Will a Robonaut replace an astronaut?
I see potentially a Robonaut going early on in a mission to get things ready for a crew, but here at the NASA Johnson Space Center, our mission is to put people in space, and Robonaut's job is to help people either before they get there, while they're in space, or potentially when a outpost or another facility in space is not manned. So we always see the Robonaut working alongside with people or preparing for people.
Can Robonauts play?
So we have all kinds of Angry Birds, stuffed animals around here, and he plays with those, and he also plays with balloons and all kinds of other toys. We have balls that he plays with as well. So we definitely have fun with Robonaut in addition to making him do all the work that he needs to do to support the astronauts and support NASA's mission.
Will a Robonaut ever walk?
In the future, the robot will come off of its stand, which is similar to the one you see behind us, the stand that's on Space Station. And with those legs, it'll be able to walk, or essentially climb, through the Space Station modules and even go between the modules. And then later on in our development, we'll be able to go outside the Space Station and climb along the outside, performing tasks to help the crew.
Okay, very good. Well, thank you so much for the presentation. It was very interesting, exciting, and we may have a NASA engineer in this group. You never can tell. You might be looking for this group coming through in about 15 or 20 years or so. So let's give Dr. Dippler a nice round of applause. Thank you.
Thank you.
Bye-bye.
Bye.